Finally, for our last ANOVA, what we're going to do is a mixed, so a two-way mixed design, which is sometimes called a mixed factorial. And so what you're going to be looking for is that you have at least one repeated measures variable and one between subjects variable, hence the mixed part. And so with those designs, we will look at both Levene's and Mauchly's. Remember, with Mauchly's, you need at least 3 levels. Because if you only have 2 levels, then you won't see the test. So remember, with Mauchly's, and we covered this in double repeated measures, if you don't have more than 2 levels, you will not see the test, because you can't test that assumption, or the assumption is kind of assumed to be met with only 2 levels, because remember that Mauchly's is the correlation between time 1 and time 2 and time 1 and time 3, if you think about this as times, is the same. But if you only have 2 levels, there's no way to test. There's just one correlation. It's also that the difference in different scores variances are the same, and you only have one difference score variance if you only have 2 levels. So you can't really test the assumption. You have to have at least 3. Okay. That is a quiz question that I love to ask. We're going to talk about main effects, so looking at each IV by itself, and that's where this ANOVA table becomes really helpful in figuring out what to do next. In the interaction effect, where we're looking at the conditions are significantly different from each other, the patterns are different across, patterns are different across different IVs. If you've been listening to my videos for a while, you know I have animals, and they're a zoo right now, so hopefully no barking in this video, but no guarantees. So back to what are interactions. So interactions are where the patterns of the IVs are different across different levels of the IV. And in both of the previous videos, we talk about using effect sizes as ways to tell if those patterns are different when they are in the same direction. So if I have increases across both variables, maybe one of them is increasing at a faster rate than the other, which implies the interaction, instead of one is increasing and one is decreasing. So if I want to follow up my test here, so let's say I have a main effect of my between subjects variable, and the levels are more than 2. So remember, if there are 2 levels, we only interpret the means. We don't really do anything else, because then that would be running a test twice. So ANOVA and T-test are the same thing if you have 2 levels, and so we don't want to run a follow-up test on something that's not necessary. If I have a main effect of between subjects variables, I would run an independent T-test, which is the post hoc test, and then I would follow that up with either a Bonferroni or Tukey correction. In JASP, this is easy to do because the main effects are just some buttons that you can click. So you can do Bonferroni, Tukey, I think there's also Sheffe, and 1 or 2 other ones. If I have a main effect of my repeated measures variable, I follow that up with a dependent T-test. That's the test, and then I might correct with Bonferroni or Tukey. Okay, so that's the big thing here to get, is if it's a between subjects variable, it's an independent T-test follow-up. If it's a repeated measures variable, it's a dependent T-test follow-up. For that interaction, we're going to have to split one of our IV columns. And split here could mean a couple of different things. We've talked about literal splitting and double between subjects, where we actually had to split the file into separate pieces. And then in our double repeated measures video, we talked about it's not really splitting so much as make sure that you're comparing the right combinations to each other. Now that we have one of each, it kind of depends on what the design looks like, how I'm going to have to follow that up. So I could do an independent or dependent T-test depending on which variable I decide to split on. So this is across or down. And then I would do a Bonferroni correction, more than likely, because there's no automatic option in JASP to do these. Now, if that interaction is significant, people will often ignore the main effects, and that is because that reduces type 1 error because we're running less tests. If our main effects are just 2 levels, we're not running a test at all, so interpret it. But if it's more than 2 levels, we'd have to run more tests. We might end up running just a bunch of different tests if we got all 3 effects were significant. And so I have this in all 3 of my videos, but if you're running more, if you're using 2 IVs, you're interested in that interaction anyway. So why would you work on interpreting just one of the variables? If you're running 2 IVs and you're only interested in one of them, why are you running the other one? So the reason people do these 2, 3, 4-way designs is because they're interested in those interactions usually. Or in the case of like a test of the design of the study, let's say you looked at how counterbalancing affected the study. So if you ran one group 1, 2, 3, 4, another group 4, 3, 2, 1, and you want to make sure that that didn't affect it, then you wouldn't be interested in the interaction and you would hope that would go away. Okay. So there are some times that you might include a variable that you don't want to be significant, but you're going to have that hypothesis. So you already know that that interaction is not what you're looking for. Okay. But for 90% of what we're going to do in class, we want that interaction. So we're going to interpret the interaction and usually kind of ignore the main effects. You can do them. This is a Dr. B thing. It's not always true. Often people do this, but it's not 100%. So do what your advisor wants, and then you can decide if you're past that point, you can decide like, okay, I only want to run this or I only want to run that. Be sure you follow up with the correct test type, so don't run dependent T on a between subjects factor. JASP makes that a little hard to do. You can still do it, but it's a little bit more difficult to make this mistake. All right, so in the double repeated measures video, we talked about some research of mine, which is looking at judgments in memory. And so we're interested in how they are able to make a judgment. So what we do is we ask people to do Family Feud kind of in reverse. So if I say, how many people out of 100 would say cheddar if I said cheese? So that's the same idea as Family Feud. So if I said cheese, how many people would say cheddar? That number is actually kind of small. But if I flip them, if I say how many people out of 100, if I said cheddar, the next word would be cheese, that word's actually quite large. So it's like 80%. Whereas cheese to cheddar is like 10%. And so it depends on which direction we're going. We're either going forward, which is FSG in this data set, or backwards, which is BSG for backward strength. So we're going to use the repeated measures 2 data, but we're going to look at some of the other columns in it. So if you've watched the double repeated measures one, we looked at the interaction between forward and backward strength. Now what we're going to do is just focus in on what's happening with backward strength. So we gave these 2 different groups. So the regular judgment of memory task, which we call JAM for judgment of associative memory, because we like cute acronyms, versus a debiasing condition. So we're trying to figure out how to make their judgments better. So we debiased them. And that's just a set of instructions on how can you do well in this experiment. The group variable was between subjects. They only saw the regular instructions or the debiasing instructions. The BSG variable is repeated measures or within subjects, where they saw both low related words and high related words. So we manipulated what types of words they were seeing, pairs, where some of them don't have a very high backward strength and some of them have a high backward strength. So for example, on and off are high forwards and backwards, but like cheddar cheese is one that's only high backwards. And that's repeated measurable. Repeated measures, they got all of those types of words. We created an average score for low and high, and those are the ratings of those word pairs. So it ranges from 0 to 100, and these are average scores so they can have decimals. So let's get started looking at data screening for this. And it's this RM2 ANOVA data. And one thing I know I'm doing is I'm referencing other videos that you may or may not be watching due to the nature of the selection in this class, or if you're just another researcher trying to learn how to do this in Excel or JASP, feel free to ask questions in the comments so you maybe don't have to search through another video to find the answer that you're looking for. Alright, so I'm actually going to get rid of all of these columns. So the subject variable was just so that we had it. And these are the 4 repeated measures columns that we used for our double repeated measures. And then these 2 columns here are the ones we're actually interested in. So they're an average of the forward strengths for those conditions and the forward strengths for low and forward strengths for high. So I'm going to save this file as mix2 ANOVA data screening and save it as a regular Excel file so I can use the tabs. Now that I've got this saved as Excel, I'm just going to get rid of these columns because I don't need them for this analysis. So this is our master tab where we have everything and we don't touch anything. So let's try now making our no typos tab and see if we have any typos. If we don't have any typos, we'll just change this to see about missing data. So we're going to work through data screening. First thing up, accuracy. In this case, I both have accuracy for a categorical variable and continuous variables. So let's try those continuous variables first. Let's click Data, Data Analysis. I'm going to hit D on my keyboard to go to Descriptive Statistics. Click OK. Highlight our 2 columns here. Labels in the first row and Summary Statistics. So this is our accuracy page. Let's see what we got here. Obviously, I have a difference in means here. And let's make all of this bigger. There we go. We can also look kind of at our standard deviations. So this will kind of give us a hint at the beginning about homogeneity, but not by group. That's what Levene's test is for. So we'll come back to this. But you can always look at all of this. I know we generally focus on our min and our max, but you can look at these and see if anything just seems like wildly crazy. By wildly crazy, I mean means that you don't expect. So that's going to be a little tough when you're looking at my examples. But once you get the hang of looking at your own data, if you have a 1 to 7 scale and suddenly you have a 8.5 mean, something's wrong. Or if you have a 1 to 7 scale and you're expecting a mean of about 4 and the mean is 6, something might be wrong as well. I also can look at my standard deviations and make sure they're not either way too big or way too small, and that depends on the scale of the data. So on a 100-point scale, 10-point standard deviation in this study is not unusual. If I had a 2-point standard deviation, I would be a little concerned because I know that on a 100-point scale, that's going to be very, very tiny. And so we've talked a lot about good variance and bad variance this semester. So good variance is based on the manipulation in the experiment, your IV. Bad variance is the error in your experiment, which often is thought of as like participant differences. And so obviously we won't want a ton of bad variance, but having absolutely no variance in a study is also bad. So if the standard deviations were essentially 0, you don't have any variance to work with. It's hard to split it into good variance and bad variance if there's no variance at all. And sometimes that's hard to convince people because they just think about variance being a bad thing. Because we talk a lot about it being precision. So how well we've measured our variables, and we want to measure our variables very well. But for example, I was working on some studies where they were looking at answers on one of these Likert scales, and everybody picked 4 or 5. And that made it really difficult to work with that variable because there was almost no variance. So I know we talk a lot about good variance, bad variance, but I don't mean that we shouldn't have any variance because then we'd have nothing to work with. So if you think about good variance and bad variance as cookies, where you're delving up the cookies and you hope they all go to good variance, you want at least some cookies there to work with. Anyway, let's look at min and max. It's well within the range of our study, so 0 to 100, so we don't have any negatives, and we don't have any scores outside the range at the top. So these scores look pretty good. The other thing I want to check is make sure my labels look okay. So I'm going to highlight the whole column and copy it. Just on the same page, I'm going to paste it. And then I'm going to click under Data, Remove Duplicates. And that's going to allow me to make sure that all of my labels look the same. And so if I had the worst thing in Excel sometimes is when you have one that's got a space at the end, it looks right, but when you do remove duplicates, it's going to show you that there's 2 of them here, and generally that's the issue. And so if you have 2 of them that visually look the same, I would say one of them probably has a space at the end. And so what you can do in that scenario is do Control F, Command F, or up here, search. Do replace. Tell it to find a space. So just hit the space bar once. Don't put anything here under replace. Just hit replace all. Close. Okay. And now when I do remove duplicates, it'll get rid of that one. Okay. That's probably the most common thing in Excel, unless you just are typing this yourself and you can't spell. Guilty as charged, spelling, typing sometimes. Like the word characteristic sometimes. What's my other fun one? Available. Ugh, if you're having me type those words, they're going to be problematic. Homoscedasticity I can do with my eyes closed, but the word available is impossible. And so that's what we're really looking for here when we look at accuracy for group labels. Is we don't want JASP or any other program to think that we have more than 2 groups here, because we only have 2. But I didn't have any problems here, so I'm going to move this over. And then I'm going to do, okay, let's see if we have any missing data. This is the next thing. We talked a little bit about keeping some notes here, because it doesn't hurt. You're not messing up your data anyway. So we didn't have any typos. No accuracy issues. So speaking of spelling, right here. Got excited, forgot the U. Now let's look for missing data. So you can hit Control and the down arrow or Command and down. And that actually will take you to any missing data points. Another nice thing about showing you this space issue. So let me go to the end of the data here and just hit the space bar in both of these cells. They look empty, but they're not actually empty. They have a space in them. And some programs do this. It's really annoying. Some programs also put dots here, which is not helpful. Okay. So as we're looking for missing data, it will just skip over that spot. And often will pretend like that's got something in it. And so that's why using our replace, search and replace for spaces, okay, will clear out maybe some cells that have some spaces up here that you just missed. Because the formula we're about to do will tell you that those are real data points. All right, so let's test for missing data. So I'm going to do equals count A, open parentheses. Okay. If you're ever not sure about the formulas we're doing, you can actually click on them and it will tell you what function this is. So count A counts the number of cells that are not empty. And that's really what we're looking for here, is anything with data in it. I'm going to hold down Shift, Control, and then up to highlight all the cells. Close parentheses. We're going to divide by 158. That's how many participants that I know I have, times 100. And I know it's 158 because I'm down here at line 159, minus 1 for the labels at the top. Go from the white plus to the black plus, drag over here, and I've got 100% of both of these data points. Now remember that we're only allowed to fill in 5% of the data across and down. And so in a case of an ANOVA, generally that means that we just have to delete the people who are missing, because otherwise we're making up their entire DV, and that is problematic. So really here, testing for missing data just allows me to say how much missing data I have, which in this case is no missing data. But I don't think I would fill any of this in because I would be making up a lot of data for each individual participant. So let's say this data point was missing, that will be making up 50% of their data. All right, so I don't have any missing data. Let's check now for outliers. So I'm just going to change this tab because I didn't do anything here. And let's look at Z for the low and Z for the high. So we're going to write a formula to calculate z, which is each person minus the mean divided by the standard deviation. So open parentheses, well, equals first, open parentheses. Click on the data point we're interested in, hit minus, highlight the whole column. Oops, I'm sorry. Hit minus, type the word average. Now highlight the whole column. Close parentheses to close for the average. Close parentheses again to close the top, the numerator. Divided by STDEV. Open parentheses. Click on the column again, close parentheses. Okay. Be sure you're hanging on to all those parentheses so that the numerator gets subtracted and then divided. Okay. So click here, we got this white plus. We're going to drag it over once we hit the black plus. Okay. And that allows it to fill in the formula for the second column. So it's just a handy cheat to make it go faster. Highlight both of them, go from white plus to black plus, double click. Now, we have a lot of data points, but we only have 2 columns we're interested in. So I could sort this column, sort that column. But remember, a faster way to look at your outliers is to highlight these 2, click Home, Conditional Formatting, highlight cell rules greater than, so this first one here, 2.99. Do the same thing, conditional formatting, highlight cell rules less than, negative 2.99. We could write this Excel formula to show us the absolute value of these outliers, essentially deleting the negatives, but I think it's helpful to know which ones are outliers on the bottom and which ones are outliers on the top. That's personal preference. So we've got these 2 outliers up here, which if you watch the double repeated measures are the same 2 outliers that we had before. And I can kind of scroll through the rest, or I can show you one more new hack in this video. So click Data, click Filter. This works pretty well as long as you don't have a ton of lines. Click the little down arrow. What you can do is filter by color. So tell it to only show you the colored ones. Now you can do both columns at once, but it doesn't do quite what you think it does. So to turn this off, you can click on it again and say clear filter. So I've got these 2 here, and I can filter the first column as well. Okay. And by color, it isn't letting me click it because there aren't any that are colored. Okay. Works the same if you kind of scroll. Since we colored them, they're very visually easy to see. So it looks like these 2 puppies are my outliers. Okay. Now, what do I want to do with these 2? So this is where I have to make a decision, and in your homework I'll tell you what to do so that we all get roughly the same answer. It makes grading easier. But let's say this is real research because the data is made up, but this is real research. What would I do in this scenario? Well, it puts me in a tricky spot because I know what group they are. And so this is one way that you have to be careful of not introducing experimenter bias in your study, is where the experimenter can manipulate the data in a way that supports their hypothesis. Right? Here, I see that these scores are very low. And I know the debiasing group is the one I was trying to get their scores to go down. So these people are actually doing the study correctly. They're responding well to that set of instructions to bring their scores down, which is what we were telling them to do. So here they're outliers because they did the experiment right, whereas everybody else may or may not have responded to the study well. So do I exclude them because they're outliers, because they clearly are, or do I leave them in because it probably helps my hypothesis and they're actually doing the experiment right? So that's a very tricky place to be. And what we ended up doing, or I don't remember if we had this exact scenario, I was trying to show what would happen, like how you could make decisions here, is running it with and without. And that's the safest way to go in that sort of scenario, so that you can say, well, they are outliers, and if we run them without, we get X, but if we run them with, we get Y, and hopefully X and Y are compatible. But Given the sort of reproducibility problems and like just kind of a data science focus right now, telling people what you did is at least the best solution, and sometimes running a little more than necessary and saying, well, we did it both ways. So even if this is my bias saying leave them in, it worked with leaving them in or leaving them out. So it's just not misleading people about what your data is. All right, so small research methods rant aside, let's leave them in. They are outliers, but they've done the study correctly, and we could always try it again and take them out and see what would happen. So I'm going to make a final data set here, which is actually the same data set I started with. Now, if you are looking at outliers and it is quite clear that they're outliers because they're dicking around in your study, delete those people. That is a case where I always say if it's clear that they're just making patterns in the data or they're just hitting 7 the entire time to end the study quickly. So any type of research software that allows you to look at how long they were taking, like survey data, if it took them 2 minutes to do a 30-page survey, get rid of that crap. Because we don't want garbage in our data. This, however, is a scenario where the outlier isn't garbage data. It's data that is true, but maybe because only 2 people responded well to the manipulation. Okay, so final data set. Let's focus on our assumptions now. So we've looked at outliers, and we had 2 outliers, leaving them in. So now to look at our assumptions, the first thing we want to check is for additivity. We just don't want these 2 columns to be perfectly correlated. So I'm going to click Data Analysis, go up to Correlation, hit OK. Highlight these 2 columns, labels in the first row, and then just hit OK. So that gave me the correlation between these 2 columns, where this is the one I'm really interested in. Remember that these are automatically going to be 1 because that's correlated with itself. And so that's fine, you haven't done anything wrong. And we're just trying to make sure that the things that aren't on the diagonal here are not 1. For repeated measures data, we expect high correlations generally because it's the same people tested multiple times, and especially in our study. Sometimes the correlations get up to 0.9. And the normal rule for additivity is 0.9. But the rule for repeated measures additivity is that it can't be 1, so 0.999. So essentially you're just trying to check here that it is not 1. Otherwise, mathematically, this does not run. So this looks okay. Now we've checked additivity, let's go on to normality, linearity, homogeneity, and homoscedasticity. So I'm going to create my random variable. So, sorry, I got excited and I did that kind of fast. So equals RAND, open close parentheses. And I double clicked to get everything to fill in. And now we're going to run a fake regression. So thankfully this is our last univariate ANOVA video. Okay, we will cover a little bit of multivariate ANOVAs. So this thankfully is the last fake regression for regular ANOVAs. When we get to regression, so real regression, we won't be running anything fake. So we won't have to do this step. So let's click Data Analysis. Typed R to get down to regression faster, so let's use regression here. Okay. I'm going to highlight all of my random data. Now remember, I've been having trouble when it has the labels in the first row. You may not have that problem, but I'm just going to avoid the labels. For X here, I want to highlight all my real data. So I'm doing Shift Command or Shift Control down just to highlight everything kind of quickly. I want the standardized residuals and residual plots, and normal probability plots. Click OK. Okay, so here are our assumptions. We're going to ignore this stuff because because that's not part of our analysis. Kind of move everything around here a little bit. I always do normality first. Oops. Just kind of make this bigger while I can still see it, because for some reason Excel just gets angry with me the more I do on this page. So we'll make this just a touch bigger so you can see it. Now to do normality, what we can do is just highlight the standardized residuals and use the histogram feature. But we talked a little bit about across a couple of these videos now that histogram, the x-axis is funky. So what we can do is to create our own x-axis first. And I'm just telling it what the bins I want to use are. So I'm doing -2, -1.5, -1, so I'm counting down by halves. You can also highlight all of these after you get a couple of them in there, and Excel will recognize the pattern you're using. So I'm dragging and dropping here so that I get from -2 to 2, because that's generally where the data is going to be. And that just allows us to create a bin range that will force the x-axis to look like something we're interested in. Now click on Data, Data Analysis, and Histogram. Click OK. Our input range is the standardized residuals here. Our bin range are the bins that we just made. So here, excuse me, I want to see the chart, and then I like to stick the chart. Gracious Excel, have a fit. Just kind of right here. Just so it's on the same page. You can tell it to be on a different page, that's fine too. So it created those bins for me, and it added this helpful more category with nothing in it. And then it hid the plot somewhere up here. So let me drag this down here. This is where Excel tends to go. So let's see if we can force it to not do that. And I just made the chart a little bit taller. So this is looking okay, right? Remember, we want it to be centered around 0. So it looks to me like it's got a little bit more data over here, because this goes all the way to 2 and this one does not have any on 2, but centered around 0 with the tallest peaks in 0. So we've got a little bit of bimodal stuff, but it's not too bad. So we generally want this to be kind of one big hump. We don't want anything to be skewed, so maybe a little bit of skew here. But it's very small because it goes all the way to 2 over here, and there's a little less data in the tail over here. Okay, so I see the difference in heights here. I have at least 30 people, and I have at least 30 people in each group, so I'm probably okay. Okay, so remember, for normality, we can bend that assumption and still get a fairly accurate error as long as accurate answer, excuse me, as long as we have at least 30 people. That's the central limit theorem. All right, let's look at our linearity plot here. So at trend line. And that looks pretty straight. So this plot is fairly straight. The dots are lining up pretty close to the line, so I'd say that looks okay. Now I can look at each residual plot individually, and this one's got quite a bigger spread than this one. But if I look at the 0 line horizontally here, everything appears to be fairly even between the two. And then if I could look at the middle of this graph, everything is fairly centered around the middle. Here, still kind of spread evenly and centered around the middle, but we've got a couple of dots down here that aren't hanging out with the rest of them. So they're kind of starting to clump together. Right, so clumping over here, less clumping over here. So that's not a good way to have a spread. So this way, they're about the same, but this way, they're not. We can create a graph of them together. So what we want to do is highlight predicted Y and our standardized residuals. So that doesn't always work in Excel, so I usually have to highlight all of this together. and then delete the residuals. So that I have predicted y next to standardized residuals. I don't know if it would do anything weird if you deleted this one, since the graphs are sort of made with those, but I just copied them again. I'm gonna highlight all of those. Go to insert. Oop, not a chart, bar chart, sorry, a scatter plot. Okay. And that gave me my standardized residuals here versus y. So I'm not entirely sure why the y-axis here is being so odd. I'm sorry, this is the x-axis. So what I could do is format that x-axis. Okay. Found that very strange. Oops. Come on, give me my format sheet. Right click, format axis. Let's make that minimum 0.3. So that, for some reason, was controlling the axis for us, which is a little odd. Okay. Now, are they centered around 0? Well, a little bit, yeah. So this gives us a better range of the data, understanding that range. And yes, mostly between 2 and 2. In the middle here, so this is where we start to have some weird clumping and then some extra dots kind of off here to the side. So this is a little problematic. So homogeneity, we'll see, is what I'm trying to say. So homogeneity, remember, is the one centered around 0, and then this way centered around the middle. And it's not good that there's a weird gap here, and that most of them are kind of clumped together, and then we have some extra ones out here. For homoscedasticity, it's just the spread is even, and I would say, minus these two little obnoxious dots out here, the spread is fairly blob shaped. So this is the one where you pretend to draw a line around it, and you don't want any UFOs or triangle shapes, Dorito chips. Like, you don't want the spread to be small on one side and large on the other side. All right, so I'm going to save my Excel chart here. I'm going to take my final data, so the first column's not the random column here. I'm going to copy that. Create myself a new data set, so paste, and save that. So file, save as. I know I didn't delete anybody, but it's just easier to make a new data set. Be sure you save that data set as a CSV. And what that does is it allows me to have my sort of final one, which is separate from the repeated measures 2 data that had the extra columns in it. And I'm going to say don't save because for some reason I don't know why it asked me to save. I'm going to close this one as well. I'm just going to close Excel. So I've got my mix 2 ANOVA. That's nice. And I'm putting the J on the end for our JASP group. And we're going to open JASP and now finish testing our assumptions. All right, so I'm going to click File, Computer, figure out where you have that saved, that data set we just made, so mix 2 ANOVA. So now my group variable and my 2 repeated measures variable. So here's the between subjects variable, my 2 repeated measures levels, and the dependent variable here is rating. So we're going to click ANOVA, and anything with repeated measures here has to go through repeated measures. So click repeated measures ANOVA. We're going to take our group variable and stick it down here in between subjects factors. Our BSG low and BSG high, we're going to stick over here. First, I'm going to label these. And that just helps us see them over here. So now see how it says BSG group. Hey, don't go away. So click ANOVA, repeated measures ANOVA to get that screen back. Just was trying to show you that it labels it over here. I'm going to say level 1 is low, level 2 is high. And that just makes it a little easier for you in the output. We'll put low and high in the appropriate places over here. It's going to auto-update my ANOVA over here after it runs. And then let's click on assumption checks. We'll click on sporicity, but it will give us the NaN, meaning, I'm not really going to test this because it only has 2 levels. And then now we can click on homogeneity, and we'll get Levene's test for each one. So I've run all of my tests here. Let's see what happens. So first, let's look at assumptions. The assumption of sporicity is not something we can check because we only have 2 levels, but we can check for homogeneity. And homogeneity was a little suspect on our chart because it wasn't spread evenly across. It was up and down, but maybe not across. And that's probably not due to this one, right? BSG low, the p-value is 0.08. This is an assumptions check, which we're going to use 0.001 as our rule. But BSG high here is pretty much right on the money as a problem. So the variance here is not necessarily equal across groups. So for our high level, repeated measures level, we do have maybe an issue with homogeneity. And that is what we saw in our residual scatter plot. How would I deal with this? Well, I might consider eliminating my outliers because that's probably part of the problem and testing this again. But then you might be able to do some other types of ANOVA or corrections on ANOVA for high homogeneity. Given, fixes up for Levene's, then I would look at my ANOVA here. So here, everything for the width of repeated measures variable is going to be within our within subjects box. And so our BSG variable here is significant. Okay. So there is a significant effect of backward strength between low and high. BSG by group interaction is not significant, which sucks. We're going to pretend like it is to follow up on so you can learn how to do an interaction post hoc test, but it is not in this particular case. And then our between subjects effects, the group variable here is also significant. So it separates them out into 2 boxes, and that's because of just the different error terms that you're going to be using. And so anything that's repeated, it goes here in our within subjects box, and then anything that's all between goes here in our between subjects box. Okay. And so you got to look for all 3 p-values. Okay. We were on repeated measures ANOVA here. Good grief. I keep clicking away from it. All right, so I've still got my same analysis. I'm just removed the extra one. Now, if I were following this up for real, my BSG is significant, but it only has 2 levels. So it gives me the option to do these post hocs here, but since I only have 2 levels, I wouldn't really want to do them. So I'd actually just close that up. Now, under additional options, we can ask for our descriptive stats, which we really need, and our estimates of effect size. In one of the last videos, I talked about this being partial, but you really have to click partial to get the partial one here. So that's a mistake in one of the previous videos where I clicked on full eta and then I was like, oh, this has to be partial. That's because I thought I clicked on partial and it's not. So be sure you click on partial eta here, which is the normal thing to present. If you click on full eta, that's fine. Just be sure you report them correctly. And that's just a mistake I made in the last video because I wasn't paying attention to what I was clicking. Okay. All right, here. So we've got our full and partial eta. So look here, these 2 are the same. Well, they're the same because the denominator ends up being the same for these. So full and partial for this between subjects effects ends up being the same. And they're pretty close here, but they're not exactly the same for repeated measures. All right, so let me look down in here at my descriptives. The descriptives box here, unfortunately, gives me the condition means. So if I wanted my level means, so this BSG thing is different. In the double repeated measures video, we just kind of averaged them. But in this particular case, it actually is easy to get BSG low and BSG high. You can click descriptives, descriptive statistics, and just ask it to give you the descriptives. So for BSG low, they're rating them about 64 points. For BSG high, they're rating them about 78 points, and that's why it's significantly different. Now for the group effect, I would kind of have to average these. So our debiased group, so we've got 60 points and 72 points. You guys know I'm bad at basic math, but that's about 66 as the average. For our jam group, we've got 68 and 82. It's about 14-point difference. So add 7 to 68, 75 average. So the difference between those groups is that we're talking about a 66 to a 75. So our jam group is rating them higher than our debiased group, which is what we expected in the experiment. Now, this interaction is not significant, but if it were, what would we do? Okay, so going back to my repeated measures ANOVA box, which means I'm going to remove that analysis again, just so I don't have it 3 or 4 times in my output. There's not really an option for me to do post hoc tests for the interaction. I could make a plot, which would just allow me to see what that interaction looks like. In this case, the lack of interaction. So let's make this plot. Okay. And look how perfectly linear, parallel those two lines are, and that is why there's no interaction. The pattern of the differences is the same. So no interaction here because the pattern, these two lines don't cross. But if we wanted to analyze this is where we're going to talk about across versus down. Okay. So I'm going to make a little table. Okay. So I've either got BSG low or BSG high. And then I've got my jam group or my debiased group. Okay. And so that creates combinations like this. Okay. And so these are the conditions in here. So I could analyze this going across. Oops, put that in the wrong place. Sorry. I could analyze this going across this way. Well, if I analyze it going across, I'm focusing in on BSG low, and I'm comparing jam to debiased. When I compare jam to debiased to each other, that's actually independent T, which seems counterintuitive because this is, it seems like that's the repeated measures variable going across. But when I focus in on that repeated measures variable, it's an independent T test because what I'm actually comparing is jam to debiased. So the comparison here is holding low constant jam versus debiased is independent groups. So that's true here as well. Now if I'm going to go down, going this way, I'm looking at just the jam group, low versus high, that's a dependent T. Because they both, participants got low and high words. Okay. And so this sort of chart may help you figure out which type of test to run. Because it seems like, okay, I'm going to pick BSG, so I'm picking BSG, so it must be dependent T. And that's actually not true. So whichever variable you split, so let's just take some notes here. Whichever variable you split, the other variable is the one you analyze. Okay, so that means if you split on a repeated measures variable, you analyzing the between subjects variable. Ugh, can't type. So it's independent T. Right. And if we split on this variable where we look at just low and then just high, we're running independent T. If we split on the between subjects variable, you are analyzing the repeated measures variable, so it's dependent T. So just sort of use this as a guide on which one you're doing. Okay. And this is only in the case when you have a mixed design, a simple mixed design. So how do I know which way to go? Okay, and I talked about this a couple times as a cross or down. Okay, right, so the first rule is go with the hypothesis. Okay, you might have a specific hypothesis for your experiment, or split on the smaller number of levels. Okay. I'm sorry, split on the larger number of levels, which creates less tests. Okay. In a square design, that doesn't matter. Okay. And by square, I mean it's a 2 by 2, 3 by 3, etc. Okay. And in this case, we do have a square design, so it doesn't really matter. In the double between subjects video, we had a 2 by 5. So 2 for one level and 5 for another. And so we split on the 5 to create the smaller number of post hoc tests on the 2. It takes you a little bit longer to do the splitting, but it's way less tests usually. And then the real rule is, remember, do what your advisor wants. But this set of rules about going with a hypothesis or splitting on the larger number of levels is from the Keppel and Wickens book. Okay, so in our case, we could do either one. If, however, you're using JASP and you have more than two levels of the between subjects variable. Okay, so this is kind of an important qualification here. No matter what you do, pretty sure you're going to have to need to split up the Excel files. Comparisons. Okay. So specifically here, what does that mean? Let's say I have 4 levels of my between subjects variable. So this is all an example. This is not the one specific example here we're doing here. Because we're going to be running t-tests, remember in JASP, the t-test can only handle the fact that you have 2 levels. So what you would have to do is either split on, I'll make this. Either split all 4 levels into separate files, then analyze dependent t on the repeated measures variable. I would say this is the easiest solution. Or split into what we're going to call pairwise comparisons. Okay. And analyze with independent t. Okay. So what does that mean? That means I would have one Excel file with levels 1 and 2. One Excel file with levels 1 and 3. You're going to see this is going to keep going, right? So one Excel file with levels 1 and 4. And that was going to end up being 6 files in total. 1 to 2, 1 to 3, 1 to 4, 2 to 3, 2 to 4, 3 to 4. Okay. So that's why I think this one's the easiest, because I split it into 4 separate files, and then I analyze my dependent t on the repeated measures variable, whatever that is. Okay. Otherwise, I have to split them into files where I only have 2 levels. Okay. And so this is actually true if you're doing double between subjects, unless you have a 3 by 3 ANOVA. And so you have to kind of split up the Excel files manually for yourself. In this particular example, we could go either way. So I could split into 2 separate Excel files here and do low versus high for jam and low versus high for debias. Or I could run an independent t on just BSG low and just BSG high. And that's actually the slightly simpler solution. And that actually was what matched our hypothesis. So that's what we're going to do. Okay. Now, if I wanted to do it the other way, what I would do is create myself a jam Excel file, and then I'd run this dependent t, and then a debiased Excel file, and I run that dependency. This way, what we can do is we don't actually have to create any separate files because BSG low and high are already separate variables. Okay. That only works because I have only 2 levels. Okay. If I had 3 levels, we would have to do something else. All right, so that was a really long way to go about talking about t-tests. So we're going to do an independent samples t-test. Our group here is each of the debias versus jam conditions, and I want to actually compare both repeated measures for it. Let's see, I want to click not mean difference, I'm sorry, effect size, so we get Cohen's d. So this is independent t, it's just Cohen's d. And I can get my descriptives, but those descriptives are the same ones I have above. And so that's what I had to do for the post hoc test. All right, remembering that this interaction is actually not significant, but this is just to show you how to do it. Let's copy all those results, stick them down here on a new page. Let's tell those to keep source formatting. There we go. So it doesn't come up in Calibri. Heaven help us all, Calibri. So let's talk about how to write all this stuff up. I'm actually going to come down here to sporicity and Levene's test first. And I'm just adding the page breaks so that they're a little easier to read for you later. You don't have to do that in yours, but let's say we wanted to write up Levene's test. Because we can see that it's clearly significant. One of them is significant and bad for us. So I don't know why this is like weirdly spacing so large, but that'll work. So for our low case, it is 1 and 156, so this degrees of freedom here, equals 3.02. Perfectly dyslexia'd that, 3.02, there we go. P equals 0.08, and this one is not significant. For our high BSG level, it's 1 and 156 again, it's 10.83. P equals 0.001. Now, we've been talking about P needs to be less than 0.001, but this is so close, I would probably say that's significant. And so we'd have to find something to do. So I might say, let's go look at outliers again, delete those 2 outliers, try it again without those outliers. Nothing to do with sporicity because sporicity is only 2 levels. Come up here, talk about all of our ANOVA effects. So for the main effects, remember main effects are with 1 variable only, so each IV by themselves. BSG is significant, okay. So it's 1 and 156 equals this 258.34 right here. Our p-value is less than 0.01. And I'm going to use partial eta squared. And this one, I tend to like the p here, but I don't think it actually matters. It's 0.62, so this is a very big effect. Why this isn't bold. Our main effect of, okay, computer's being weird here. This is our main effect, sorry, of the group. Okay. So what we've done is we've looked at this one here. Now we're going to come down and look at this one here for our other main effect. Okay. Each variable by itself. 1, 156. So 1, 156 here and here. Our F is 3450. Again, our p-value, I'm just going to kind of cheat here, cut and paste. Careful cutting and pasting though, be sure you fill them in correctly. Is less than 0.001. Our eta squared here is 0.18. Okay, so still a medium to large effect. Now if we look at the interaction, the interaction is here, this one. It is not significant. Okay, so it is f of 1 and 156. They're not all perfectly equal like that, but if you are doing a square design, 2 by 2, 3 by 3, they will be usually all the same. That f value is 1.28. Our p-value is actually equal to 0.26, so it is not significant. I'm trying not to bold. There we go. Copy my symbol here. And this eta is 0.008. Okay. So I could round up, or I could just say 0.008. So you can use 3 decimals when they're really small like that. All right, so just italicizing. If it's a letter in a statistic, it's in italics usually. So I would say my main effects were significant and my interaction is not. If I want to look at my post hoc tests, so just kind of pretending here that our interaction was significant. Come down here to my t-test output. Oh, their means are down here. I can use those. Okay. And I'm going to create my little table here. So IV1, Group 1, Group 2, test D interpretation here. So this is IV that you're splitting on. So we're just going to call this IV1. We're going to call this Group 1, Group 2, the test statistic, the effect size, and then our interpretation. So for our first IV, it's BSG low is what we're testing. Group 1 here, we can do this in either order, but I'll do it in the order of the table. Our debias group, the mean, let's turn off double spacing so it's all in the same place here. There we go. So our mean is 5989. Our SD here is 1278. In this case, we do have a specific n since it's independent t of 74. We're comparing that to a JAM group of 6827 with a standard deviation of 10.84. And our n value here is 84. So the n's are not perfectly equal, but we still have fairly large sample size. Our t-test statistic here is going to be up here, so it's this first one. So we have 156 degrees of freedom here. T is negative 4.46. Our p-value is less than 0.001. Our effect size equals, I could hang on to the negative if I wanted to, but it's not so important, 7.1. Okay, so that's medium to large effect. Hold on to interpretation for a second. Our BSG high group, we're going to do the same thing. So it's t-bias. Our mean is 72.44. Standard deviation is 12.93. N here is 74. Versus JAM, mean is 82.72. Standard deviation is 8.29. Quick N here is 84. Quick programming note. See how the standard deviation here is 13 and the standard deviation here is 8? That's part of your problem for your Levene's test. It's because the variances are not equal. Our t-value here with 156 degrees of freedom is 6.01. Oops, negative 6.01. P-value is less than 0.001. Our effect size is negative 96.96. Now, how would I interpret these? Well, remember that this has no correction. So your t-test output has no correction on it. And so what would I do if I wanted to correct? Well, the easiest thing to do is to do a Bonferroni test in this particular scenario, because that is a correction on alpha instead of being a correction on P. Okay. So I could do a Bonferroni correction. Okay. And the way that works is we're going to take our alpha, remember this is type 1 error, we set this value, which is usually P less than 0.05. Give my computer here a second to catch up to me. Okay. And then we're going to divide by the number of comparisons that we ended up running. Now, people think about this as P, but P is the statistic that you found in your study. Here, this is alpha. This is a P cutoff, if you will. So we're going to take 0.05, which is the criterion we normally use, divided by 2. That's 0.025, which is our new alpha. And we're going to compare that value to P, found in the experiment. Okay. So here, my interpretation is that P is less than 0.025, so I would say this one is significant. Because P is less than 0.025, I'll just write that. Because P found is less than alpha, our new alpha. Okay. Same thing here. Now there's no interaction in this study because these are approximately the same effects. Okay. So we're going up about 9 points here, we're going up about 10 points here. That is the same pattern of data. The effect sizes are roughly equal. Okay. And so the interaction is not happening because we have that same pattern between these groups. Okay. They're moving in the same direction at the same speed. Okay. And that's easiest to see in a graph like this. When you have parallel lines like that, that means there's no interaction usually. Okay, so we've gone through kind of everything from data screening to running the test, running a post hoc test if you were going to run one, if it was significant. Let's make a publishable worthy graph, because while I love the graphs that JASP give you for just comparison purposes, you couldn't really publish this sort of thing. So let's come up here to where I have my write-up, okay, and let's just make ourselves a graph to use. So let's see, figure 1, and it's going to be means and 1 standard deviation error bars. So I'm going to go ahead and tell them what type of error bars I'm going to give for each condition in the experiment. So let's pull up Excel. I'm going to close JASP just so my computer maybe won't have a fit. Okay, go back to using Excel. Okay, click here. Come on. And let's try to make that graph. So we have got BSG's low versus high, and then we've got jam versus debias. And we're going to do that same thing, so this is going to be our means. We're going to do the exact same thing down here and do standard deviations. Just kind of moving this over here. We can pull these from our table that we just made, or I can pull these from the descriptives box. Excuse me. So for low in the, well, I probably should have done these in the other order, but 59.89. And then low jam is 68.27. And then we've got 72.44. Just trying to make sure I match them to the right box here. 82.72. Yeah, 12.78. Versus 10.84. And then 12.93 versus 8.29. Let's highlight this, see if we can get our chart here. So insert, cluster column graph. And let's spend some time cleaning this graph up. So we're going to get rid of that chart title and get rid of these ugly bars, these lines here. We're going to add horizontal, vertical axis titles. We're going to move this thing here. If you've watched my double repeated measures, we're going to talk about how to add a legend title, because I cannot figure out how to do it as part of the graph. And so one thing we're going to have to do is kind of move this around a little bit. Just kind of manipulate the sizes here so that we can get our legend somewhere kind of out of the way, that we can still keep what's called the ink to or print to type ratio kind of low, so that we don't have these huge excess spaces here. Everything is on the chart, so we can change the font now. Times New Roman 12. And so if you have just the whole chart selected, it'll do everything at once for you, which is really nice. I can go ahead and add my error bar so we can manipulate where this is going to go. So I'm going to click here on the first set of columns, and it's highlighting going across. Okay. Now we've talked a little bit about, like, how do I know which way to present this data, and I would argue this is probably not the right way to present it, because we didn't compare the two jam conditions to each other. Instead, what I did, so I'm going to click Chart Design, switch row and column, is actually compare the low BSGs to each other and the high BSGs to each other. So I did this comparison and this comparison, not jams low to high. So I always try to make my graph match the type of test that I ran, because then it's like test 1 is here, test 2 is here. That's not a hard and fast rule. It's just a nice way to make it match your output. And anytime that your results section matches your picture, people can read it much easier. Okay. And that actually does, because of the bars, give us a little more room to put our legend over here. Okay. Now, if I click on this bar, it's highlighting going down. So I want to click Add Chart Element, Error Bars, More Options. Pop up over here, custom, specify value, highlight, go down here, click on this thing right here, highlight going down. Remember, do the same one twice and they should be the same on both sides. Click this thing here, so it's highlighting here, so we're going to highlight the same thing down here. Add chart element, error bars, more options, custom, specify value, highlight, and highlight. Remember, check that they're the same, hit OK. Okay. So this is looking pretty good. I'm going to change my axis titles. So this one down here is BSG backward strength. I might just call it BSG level. The y-axis here is the rating. So it's our average rating. And then I don't have up here a label for my legend, and I cannot figure out a way to make Excel give me that kind of label without just adding something manually. So what I did last time was I clicked Insert, Text Box. Just kind of told it to stick a text box right here, and then I called this Instruction Group. And you can kind of manipulate how that looks. And then because Calibri is this default, we're going to change that to Times New Roman and 12 so it's all in the same font family. And you'll notice as you do this that it actually, they make all the font stuff here a slightly different gray. So we'll fix that here in a minute. Other thing I want to do is fix the axis bar. So I'm going to click on the axis, click on the paint bucket here, and get fill, or line. Sorry, line. Solid line, change that from blue to black. Okay, click here. Tell it to be a solid line as well. So that just makes the graph look much more readable. We're going to click on the chart design, change colors, and make it grayscale. Okay. So we spent a lot of time on graphs, but I think graphs are pretty important because you don't want to mislead people about your data by having a graph that's inappropriate for the data. Okay, I hit the wrong button. Control C. My y-axis length is okay. So it's 0 to 100, which is what the data is. I'm going to paste that into Word. You can actually make these graphs directly from Word, but it opens Excel anyway. So just figure I'll just do it in Excel. Blah, blah, blah. I'm going to paste this into Word, and then I'm going to manipulate what it did to it. So click down here when you get this little paste thing. Keep source formatting, okay, which is helpful. Now I can actually change this all, oops, not the text here, the text to be black. Right? And now the text is all the same color, which is kind of nice. Otherwise the legend label stuck out kind of like a sore thumb. And the other thing I want to do is turn off a stupid border that it adds automatically. So chart design, sorry, it's under format. Legend, the little line, pencil looking thing here, shape outline, no outline. Okay. So I don't know why under keep source formatting it doesn't turn that all off, but here's our figure. So this is much nicer, publishable figure. Okay. Now when you're writing this up, what you're going to have is make sure, so these numbers are going to be just a touch different here because this is an old write-up. You're going to make sure you have all of your F values. So I've got 1, 2, 3 Fs, any means that you want to report, and then you might talk about your post-hocs tests here. So dependent T with a Bonferroni correction, and so then I would report my T values because I have them in this case. This is an old example from SPSS where you do not, or not SPSS, I don't even remember. This is an old example where you don't get the T values, but we have them, so we would stick them in there. In our case, we did an independent t-test, so I'll rewrite this so it matches our example, but this is an old example. At least have those 3 F values and your post-hoc tests, and then a very brief description at the beginning of what you did data screening-wise. Last but not least, let's cover power, and then this video will be over and we'll be done with regular ANOVAs. Okay. Got a small party. We're going to choose F test as our test family. Under ANOVA here, it's repeated measures within between interaction. Okay, so this one here. We're going to estimate that effect size. And so in this example, I did the effect size as a large effect, so eta 0.25. So I'm going to click determine, then direct. Let's estimate that as large, so 0.25. Calculate and transfer to main, so that's going to change the F over here. Alpha is 0.05, power is 0.8. Our number of groups here is the number of levels for our between subjects variable. Our number of measurements is the number of levels for our repeated measures variables. Okay, so 2 by 2. And actually, denominator, yes, okay. So it's a 2 by 2. Our correlation among repeated measures, we can leave that as 0.5. We know that it was like closer actually to 0.6, but if this is completely beforehand, 0.5 is not a bad estimate. And our non-sporicity correction, or our epsilon, would be, in this case, 1, because we only have 2 levels for a repeated measures variable, so that there's no way to fix that one. And it says that we're going to need 10 people, which is what I got out here in my output. Now, if I wanted to estimate from this study, how many participants would I need to find a significant interaction given the results from this study, I would change partial eta here to 0.008. That's the one we found in the study. Calculate and transfer to main. And if you're like me on a Mac and you can't quite get to that calculate button, you can click in any one of these boxes and hit enter, and it will automatically calculate for you. For some reason, depending on your resolution settings, sometimes you can see it and sometimes you can't. Okay? And you can't resize it. So I would need 250 people to find that small interaction effect. And I only had 158. So I don't have quite enough power here to find that interaction if I really believed it was there. Given how parallel those lines are, I don't know that I believe that interaction is real or worth going through all the trouble for of a very small effect. Okay. All right, so we started this video with assumptions testing, data screening procedures in Excel. We talked about how to run this analysis, how to run the post-hocs if necessary, and then we made a graph. We talked about write-ups, and we ended with power. So now you should be able to do a mixed ANOVA and work your way from start to finish.